Hey everybody, welcome to Math with Ace, focusing on statistics today. We are talking about ANOVA. ANOVA actually stands for Analysis of Variance, and there is more than one way. There's actually one-way ANOVA, two-way ANOVA. We are focusing only on one-way ANOVA. And if you remember, the way that we started the idea of inference is that we focused on one sample. We tried to estimate a parameter for either a single population proportion or a single population mean. And then we worked on performing hypothesis tests for those two things. Then we went in a next level and we did two groups that we were talking about. We were comparing two means or two proportions in different groups. Then we went into comparing multiple proportions or groups. What about comparing multiple means? So we had the chi-squared for multiple proportions. Now we're going to be dealing with ANOVA for multiple means. And so if we're doing hypothesis testing, we are not going to use multiple t-distributions to compare and compare and compare. We're going to do a single test where we're actually going to use an F-distribution. So the key differences between ANOVA and t-tests that have one or two samples is that in ANOVA, we're using an F distribution, which, like a chi-squared, is right-tailed and positive. And what it does is it compares the variation between and within groups. So that calculation, we're going to let, in our class, we're going to care about the interpretation component, and we're going to let the numbers be run with technology. But we need to think about some key things. How do we set up the null and the alternative hypothesis? Well, in the original null hypothesis for a single mean, we had mu equal to some value. And then when we added a second component, we had mu1 equal to mu2. Well, now when we're adding more than that, we are just going to continue to add however many population parameters there are for however many groups we're talking about. So mu1, mu2, mu3, and they're all equal. Remember, this is a statement of equality. What do you think the alternative is? Typically in the past, we have done not equal to, less than, or not equal to, greater than, or less than. So those are the three options. In this case, we're not going to say mu1 is less than mu2 or mu1 is not equal to. We're not going to do any of that. We are going to have our alternative hypothesis just be that at least one of the means is different. We haven't identified which one, and in that case, you could go on to do paired t-test or do something else for that comparison. But right now, we just know based on our numbers, if our p-value comes back small, that means that we have evidence that at least one of the p-values, or at least one of the means, is different. So don't forget, you need to define your parameter. So you need to say, what is mu1, what is mu2, and so on in context. Okay. Now, checking conditions, random, independent, large counts. The beautiful thing about this being means is that you're checking means the same way you would in the past. You have that either the population stated to be normally distributed, or that the sample size is at least 30, or that you graph it and it doesn't show strong skewness or outliers. So the standard three things that we would compare for means for one or two samples. There is another condition that we're going to deal with, and that is equal standard deviation. It's actually equal variance, but we're going to check it using standard deviations. So we call this the equal SD. And what we're doing is we are assuming that these populations come from groups that have equivalent variance, where they're not one super spread out and one the other, so that we can perform our test correctly. And how we test this is the largest standard deviation needs to be less than 2 times the smallest. If this is not true, your condition is not met and you shouldn't proceed because there's too much variability here. Getting into the test statistic, you're going to go into Statlet and perform a calculation to get an F-statistic, where you're doing one quantitative variable with multiple groups, so all of the different groups that you have. And then you're going to get a p-value that tells you how likely it was, assuming that all the means were equal, that we got the sample data that we did or data more extreme, and we draw our conclusion. You could use F distribution in Statlet based on the degrees of freedom. The degrees of freedom, there are degrees of freedom for the numerator and there's degrees of freedom for the denominator. At this point, for the scope of our class, the things that we're going to focus on is we're going to understand checking conditions, writing the hypotheses, allowing technology to calculate for us, and then drawing an appropriate conclusion. Let's get into an example problem.